Okay, so hello, welcome again. So we'll continue our series on the group of self-homotopy equivalences, and Sandip will continuing his second talk, and today he will discuss on some computations for the same. Okay.
Okay, thank you. So, as the title suggests, I'll start with some computational technique for the group that we defined last time, the group of self-homotopy equivalence for a given space. Just recall that by the notation this epsilon x, we mean that this is the collection of all the homotopy class of maps such that f is a base point preserving homotopy equivalence of x. Okay, so definitely continuous is assumed because in the category where we are working is already consist of continuous maps. So just also morphisms are base point preserving as well. So for this kind of space, we want to calculate these groups. So last time we saw for x equal to, if we consider the sphere Sn or the Eilenberg MacLane space KGN, we have computed it using some basic tools in algebraic topology to get these groups. So today I'll start with another important technique, the technique of this Poussinikoff decomposition for a space, which will be useful in many other possible topological space which appears in many places. Okay, so let me start with the construction of this Poussinikoff decomposition of this space. So so the setup is we have X is connected space. Then we have a collection also. We have a collection of spaces xn for n greater equal to 0 and maps by n from xn to xn minus 1 and en from x to xn. So here maybe better this one. Just change it to n plus 1 n plus 1 to n, so that this for again n greater equal to 0, satisfying bunch of properties. So diagrammically we have this. So x is starting here, then you have to x1 to x2 and so on. Okay, so these are y1, y2 and so on. So this first of all satisfies the thing that this pi n maps, these are principal vibration. So X is a principal vibration with n plus 1. So each of these things, if we see as those are principal vibration, so what does principal vibration means? That means there is okay, but so that means there exists another vibration sequence. So okay, how to do that? Omega p prime to f prime to e prime to b prime. So the vibration is f prime to e prime to b prime. So vibration, again, recall that means the last this has homotopy lifting property with respect to any space. So that's whatever is vibration, I mean. Then given any such vibration, you consider the fiber. This f prime is the fiber of that map, and that vibration can be extended on the left, and this is the loop space of this b prime. Okay, so we have whenever we say that this is principal vibration or any space, so that means there exists another vibration sequence, this, such that we have the following diagram commutative. Okay, so xn plus 1 to xn, this 2, and this is the fiber k pi n plus 1 of x. So k pi n plus 1 of x n plus 1, that's the Eilenberg MacLane space. So here the G is the n plus 1 homotopy group of x. Okay. So this is the fiber, and we have the below maps E prime, so that these all the verticals maps are a homotopy equivalence, and this diagram commute. Okay. Whenever such situation occurs, we say that this is a principal vibration. So here in particular, we are interested in uh, this particular thing to be principal vibration. So I want this diagram to be commutative with this maps to me homotopy equivalence. Okay. So this is the first criteria. Second one that I need to have is so all this. So from these also one can see the homotopy groups of what the homotopy groups of the xn spaces that we initially took. So the other also we can from the Pn map, it says that Pn x to xn is an equivalence uh, that is induce isomorphism on pi k of x. So the induced map to pi k xn, or maybe just note it for the notation being, I just write this as pi k of pn. Okay. So this is iso on this for a less equal to n, and uh, other thing, all the yk of xn basically is 0 for k greater than n. So up to the nth level, these Pn are inducing isomorphism on the homotopy groups, which are exactly same as the homotopy groups of X. After that, all the things are 0. And so the construction is basically you just kill the homotopy groups, all the higher homotopy groups after nth level, and without disturbing the homotopy groups at the lower level. So that's the kind of inclusion of this construction. So kind of X sits as a subcomplex of this complex Xn at the each nth level. And similarly, the Xn and Xn plus 1 or Xn plus 1 again is a bigger complex that includes Xn as a subcomplex. Okay. So that's the second condition. And third one is that the diagram commutes, that phi compose Pn is homotopy equivalent to Pn minus 1. So you just see this. So here this pi1 compose P1 is homotopic to P0. Similarly, pi2 compose P2 is homotopic to P1. So all these diagrams, these triangles commutes up to homotopy. So these are the three conditions that this collection Xn, Pn, and Pin need to satisfy. So first of all, once we define the system, so first question is when does this kind of decomposition exist for a space? So that's a uh, theorem that or proposition that if pi1 x, so x is connected and pi1 x acts on the pi n x for each level, so acts on Pn x trivially, then so trivially, so for definitely n greater than 1, then such decomposition exists. Okay, so what's the action here? Pi1 x on pi n x, so it is obtained via the base point changing. So I'm ignoring on the homotopy groups the base point. So if I include the base point here, then like this pi1 acts on the pi n via the base point changing homotopy. So that's the action here. Okay, and so whenever such action is trivial, then we have the decomposition exist. So what more property does this decomposition have? That's another, like this decomposition is not just any arbitrary decomposition. This is actually a functorial decomposition. Like whenever we have a map between two spaces and corresponding Postnikov decomposition we have, then the corresponding maps also exist between each of these xn and xn prime. So that's another theorem by Kahn. It's 63. So it says that the decomposition position is functorial. So what does that means? It means that if we have a map f from x to x prime and corresponding the and those are good space. So suppose we have the corresponding this Postnikov system are this xn, pi n, and pn. So did I change the order? I write in this order only, right? Okay. Pi and p. Yeah. So this is the system for x, and the other is p n prime. So given two such system for the spaces x and x prime with the uh, with this map F, then there exists map Fn from xn to xn prime such that all the, like, so if I write draw the diagram, then such that following diagram commute or up to homotopy. Okay. So, okay. So for the space X, I have elements, let's say x2, x1, x0, and here we have x2 prime, x1 prime, x0 prime. So there are these maps. Similarly, for the other side, here you have x prime and this map. So this square and all the triangle, so this square has to commute, and this triangle already commutes up to homotopy by the decomposition rule only. But there is another possible square here via f. So f is there from x to x prime. So if I just see at the bottom, this is p0, this is f0, this is p0 prime, then it says that f0 compose p0 is homotopic to p0 prime compose f. Similarly, for each level, we also have that. Like, so instead of 0, this extra condition put that fn, pn, and pn prime. This commute up to homotopy, that square. With all extra, this also commutes. Okay. And also there is another invariant associated to one this Postnikov decomposition, that's called the nth k invariant for the decomposition. So and also there exist so when I say this, there exist fn, so these fn are unique up to homotopy. So unique, there exist unique fn up to homotopy. So this is again up to homotopy. HTTP. Okay. So this again up to homotopy. So that means whenever if there exists some map which satisfies this condition along with this commuting diagram, then this fn, if there is, then fn are homotopic also as well, and vice versa. So the other thing that this decomposition also satisfies, it takes the k invariant of the one decomposition to the other decomposition. So what's the k invariant for a for such Postnikov decomposition? So it can k invariant for okay. So it comes from the um, the principal vibration condition of the decomposition. So say that we have this map xn to xn minus 1, and it has the fiber k pi n x n, and also we have the homotopy equivalence omega b prime e, sorry, a prime and e prime. These particles are homotopy equivalence. So note that this omega of kgn space, those are these kgn space being unique up to homotopy equivalence. This omega kgn has the homotopy groups at the n plus 1th level only. And so omega kgn is kg, sorry, n minus 1, because it's only at has the homotopy group at the n minus 1th level. And what is the homotopy groups of this at the nth level? If I have pi n minus 1 of omega kgn, then using the adjoint isomorphism, this is same as saying pi n of kgn as pi k of omega x is pi k plus 1 of x. So using that, this omega kgn is homotopy equivalent to kgn minus 1. So in this case, if I want this b prime as like omega b prime as homotopy equivalent to this thing, so I should take the b prime to be k pi n x n plus 1, right? Then the omega of this thing will exactly become the k homotopy equivalent to k pi n x n, right? So b prime is basically this thing, and this if I put here, I have this is k pi n x n plus 1. N plus 1, right? So so we have a map from xn minus 1 through composing this map, this vibration map, to k pi n x n plus 1, right? So let me just this composition map, okay? So for each level n, we have a map from xn minus 1 to k pi n x n plus 1, okay? And this what it correspond to, we already have seen in the last thing uh, that this correspondence is these things are in one correspondence with the hn plus 1 of xn minus 1 with the coefficient and pi n x, right? So each such map also correspond to an unique map, unique element in the homotopy groups, in the cohomology group of xn minus 1, right? So we call this particular thing, so this map, this as the map kn plus 1, which sends this to this. So this class of kn plus 1, that is an element of hn plus 1 xn minus 1 of with coefficient at pi and x. This the n plus 1 k invariant for the decomposition. So, and so what's the relation of this k invariant with the functorial decomposition that we have seen in the last thing is that under this Fn map, if we compose the, so let me write the exact thing. So this also from the also preserves the k invariants. So in the following sense, that if star n minus 2 k n prime is the same as c k n. So again, I'm removing this class notation, just saying the kn is the corresponding cohomology element in the class. So what is this notation? This n minus 2 is the corresponding map from xn minus 2 to xn minus 2 prime, and that's the above star says it is in the corresponding cohomology groups. And what is this map? This f already, as f is a map from x to x prime, so that induce at the each homotopy group level, it induces map from the corresponding homotopy groups. And on the cohomology groups, as these k invariants having the coefficient in the homotopy groups, so this f has c, this is basically changing the coefficient group of the cohomology group. Okay, so just write in the, so it says fn minus 2 has star that is an element at the hn xn minus 2 prime with coefficient at pi n minus 1. Right, this is from x, right, this is in x prime. Sorry. So we'll have this fn minus 2 star at hn minus 2, sorry, hn xn minus 2 prime 2, because this on the cohomology it is in contravariant direction, contravariant functor. So we have hn xn minus 2 with coefficient remains. Again, some problem. This again not writing beyond this point.
So maybe you can take the boundary and write within the boundary, I guess.
Uh-huh. So I have to remove this one. Okay. Sorry. xn minus 2 by n minus 1 x prime. So this map and also the C if as map that was saying that is in the homotopy group level. So maybe the consistent notation. This is pi f, which I'm again here denoting by pi hash. So this is the map at the n minus 1th level. So n minus 1th level of, so this is pi n minus 1 x to pi n minus 1 x prime, and in the cohomology group it sends from so I want to go from, okay, right. So if as C, this is the coefficient morphism at the level for this one. So Hn xn minus 2 pi n minus 1 x to Hn xn minus 2 with pi n minus 1 x prime. So this is the changing the coefficient group homomorphism. Okay. Then finally, so k n is an element here, and kn prime is an element here. Okay, so under the fn minus 2 star, this kn prime goes onto hn xn minus 2 here, and similarly via fsc this goes to the same places. So these are the same group. So it's basically saying under these two homomorphism the kn prime goes to the kn, right? So that's the again the other functorial condition on the fn. So this all together gives a nice functorial decomposition given any space which have the property that pi1 of the space acts on the pi in on the higher homotopy groups trivially. So so from this actually we have some observation for the homotopy groups that we group of self-homotopy equivalence that we started with. So that's the goal of ours. So note that if A homotopic to G, then Fn is also homotopic to Gn. So F and G both are mapped from X to X prime, then the corresponding we have Fn and Gn, then those again will be homotopic, because if those two maps are homotopic via map HT, let's say, then at each level we have the map FNTH, and at the zeroth level that is the F map, at the Gth level that the G map, and by the unique up to homotopy condition of the thing, we also have the nth and like nth level fn map and gn map, they are also homotopic. So at each level we are also the homotopy is preserved. And so this is the first. And so the consequence of that thing is that if is a homotopy equivalence on the x, then fn, this implies fn is also a homotopy equivalence for the nth level. This is again a consequence of the homotopy equivalence, because if we have f is a homotopy equivalence on x, then there exists a map G which is inverse of that thing. Then we have f compose Gn that is up to homotopy equivalent to identity map on xn level, but fn compose Gn is also a choice for this f compose Gn. So by uniqueness, this is again Fn composed Gn. So that's why this Fn is again a homotopy equivalence for this Xn. Okay. So it's saying that the homotopy equivalences of X also reduces at the each level the homotopy equivalence on the spaces Xn. Right. So that's another observation. So third one is that this Xi, the spaces Xi, uh, or or I less than j is a Kuznetsov system for xj. Okay, so and what's the map there? So okay, again, I can't write it here. Is there any line coming?
What happened?
So is this visible properly? Like I'm seeing a line in between, green line in between.
No, 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 no. There is no green line, at least from my side.
Okay, okay. Okay, so system for this xj, then that means uh, it's too difficult.
No, maybe you can try like just close this app and reopen that.
Maybe did not try that. Yeah, yeah. Right, it's working now.
Because you switched from iPad to this now, so maybe they're.
Yeah, that's why it's taking.
Mm.
Okay, now it's okay. Now
Yes.
it's yeah, right. So yeah, so sorry for that. Sorry. So xi are positioning of system. So if I consider xi with x0 through xj minus 1, that's a positioning of system for xj, because we already have the map at each level, you know. So xj, this we have x0, x1, x2, and so on. So up to the xj minus 1th level. After that, all the remaining space I can take that to be xj minus xj itself. Okay, so these are basically after xj minus uh, 1. Those are identity map at this level. So, so I have xj minus 1 at some level, and then after that, all the maps are xj. All the spaces are xj, and these are identity map. And what are these maps? These are basically composition of these above maps. So if I have this is pi 1, pi 2, and so on. So these are composition up to all the level up to this is starting from xj. So pi j minus 1, and all the way up to pi 1. Okay, and here it just start from it need to have land to x1, so it's xj through this till pi 2. So it's pi 2 compose all the way up to pi, sorry, pi, yeah, pi j. So it's just the standard composition of the vertical maps to get the usual map from xj to xi, and we have this commutative diagram on the nodes. So that's and also satisfies all the property, because these are already from the space X itself. We have the principal vibration condition and also inducing the isomorphism, because this xi and xj, they has like this xi and xj, they have all the isomorphic homotopy groups up to the lower level, like xi at the ith level. So these all the things are satisfied the required condition for a Postnikov system. So always given any Postnikov system for a space x, the if I stick to I, or let's say any j, then below that thing itself a Postnikov system for that space. Okay, so from this thing, actually, what we see that, okay, so from this thing we get that for each level, so there is a map lower from epsilon of xn to epsilon of xn minus 1. Right, so it's just sending the corresponding homotopy equivalence to the nth homotopy equivalence that we just have seen, that if we have a map in the x level, it's sending the corresponding fn is a homotopy equivalence at the nth level. Now, as we have seen here, that xi from x0 to x j and all the above, those are already a Postnikov system for xj. So we can say like the x nth space has the Postnikov system x0 through xn minus 1, and above all the things are xn. So at the nth level, we have this map. From the xn, we can go to xn minus 1. This is the n minus 1th element of the Postnikov system for xn. So it's sending the corresponding f to just fn, fn minus 1. Right, so that's the map here. So we always have the from the higher one homotopy equivalence of the higher one space to the lower one space. Okay, and from here we have the theorem that's again due to Khan. It's in 64, that the following sequences is not exact. So kernel of rho n to epsilon of xn to image of rho n 1. So in the exactness, there is nothing new here, because given such any rho n, I can construct the exact sequence by just by taking the kernel. This is clearly an inclusion. And if I sending the map to the image itself, so this is onto, so this is already an exact sequence. But the importance of this thing is that this kernel of rho n can be identified via the k invariant of this map. So here, kernel of rho n, this is isomorphic to the following thing, that This is fn minus 1 that belongs to epsilon xn minus 1 itself, such that there exists a coefficient homomorphism fc. Uh, that means automorphism of y and x. Is that the same condition that we saw in the functorial decomposition? C kn plus 1 is equal to f star n minus 1 of kn plus 1. Okay, so this is the n plus 1th k invariant for the Postnikov system of X, and it's saying the uh, all those homotopy equivalents of this lower space xn minus 1 exist, which preserves this kn under some homotopy, like some isomorphism of the coefficient group pi n x. Okay, this is the same coefficient homomorphism induced by this fc on the cohomology group. And this is the by fn minus 1, fn minus 1 is an element in the this thing, so in the cohomology it will induce an um, morphism, and that's the condition here. So this is again kind of this kernel of rho n is again obtained from some subgroup of this e xn minus 1. So this also can be an element of epsilon xn minus 1. And similarly, this image of rho n is also identifiable to a subgroup of this exn minus 1. So that's the main point of this theorem, that e of xn minus 1 is kind of, if this sequence splits, then it is kind of obtained from the homotopy equivalence of a lower dimensional space itself. So image of rho n, this is again isomorphic to the image of gf xn to e xn. So what is this gf xn? This is the fiber homotopy equivalence of this xn with the so this is fiber homotopy equivalence of xn. So we have the fibration xn to xn minus 1. So fiber homotopy equivalence means there is a map from xn to xn which fits into this commutative diagram. So this we have the pine map. So if it's a fiber homotopy equivalence, if it is a equivalence of xn which commutes with this pine map. Okay, that's the collection. So it's definitely sits inside the exn, because any map which commutes with the extra condition is it commutes with the pine map. Even if we just ignore that map, still it is an homotopy equivalence of the space xn. So it's again a smaller subset of exn, right? So image of rho n is again identifiable to that set, and this is again coming from the homotopy equivalence of this lower dimensional space. Not lower dimensional, but having less homotopy groups. Okay. So that using this thing, Khan proved that he proved several results for this thing. So he has application. One of the useful application that he gave is that. That first, that if x has finitely many finite homotopy groups, then this Ex is finite itself. Or even if X has finite complex with finite homology groups, then also it's if X has X is finite complex with finite homology groups, then also epsilon X is finite. Okay, so this method itself, the use of this Postnikov decomposition system, not the exact sequence that Khan gave. In like besides that, also this system is useful whenever the space X has some finite number of homotopy groups. In each of those cases, various authors used this Postnikov decomposition to claim uh, the result or like general structure of this EX space. So there is a like such result by Sullivan and so Wilkerson. So they generally said that whenever X is, so that's called Sullivan Wilkerson theorem. Wilkerson theorem. So it says that if X is a simply connected space with with finite with finitely many homotopy groups. So here the relaxation is that it need not be finite. So just finitely many homotopy groups, or it is a finite CW complex, then this EX is finitely presented. So finitely presented means it is generated by finitely many elements, and the relation between those generators is also finite. So this is kind of a general structural theorem for any simply connected finite CW complex, or having finitely many homotopy groups non-zero. In that case, this is a nice result. And also for the other various product spaces, for example, the spaces which are n-1 connected to n manifold, those spaces are quite useful and appears in various contexts, that if X is a n-1 connected n-1 manifold. So I'll take just 5 more minutes, okay? Oh, okay. Uh, should I stop then? Okay, just I'll write this thing and then I'll stop, okay? Uh,
Yeah. Because I also need to go. So that's
okay,
why.
okay, sure.
Yeah.
If X is n-1 connected to n manifold, Then there is exact sequence, then sequence of this thing, sum x, so suspension b star plus I, so by n of x to epsilon x to epsilon xn. Okay, so these xn are not the usual xn that we have seen in the Postnikov thing. So this is again due to on 66. But the method use the mapping cone method. So whenever x is such n-1 connected to n manifold, then the structure of x is basically a mapping cone of, so I have n skeleton and there one. So n skeleton consists of some uh, a bouquet of sphere, um, bouquet of n sphere, and so this is bouquet of n sphere, and there is some attaching map. Let's say that's the B map here, and this is cone on Sn minus H2n minus 1. Okay, that's the, so this is the cone. So that's the mapping cone of these spaces using the map P. And there is this R map, and this is the K map. This is the R map. So explicit description of this map also can be given for this space X. And using this thing, he actually computed this epsilon of Sn cross Sn. This is a standard example of n-1 connected to n manifold, and whenever n is odd, he explicitly computed these things and gave the description of these spaces in terms of semi-direct product of some known groups. Some known groups means in the terms of the homotopy groups of Sn. And also he did it for RPN and the other CPN as well, and specifically H, the quaternionic projective space 2, he did this. For the other thing, for the infinity thing, someone else did, and for the quaternionic projective plane only, all the things are not this E of those things are not known, but for CPN, RPN, those all are homotopic to Z2. Okay, and also for specific odd cases like n equal to 1, 3, or 7, those cases also this product of the product structure, like S1 cross S1 or S1 cross S3, S3 cross S7, those things also done by other Baker Gottlieb's, like other authors. So some sort of for the Sn cross Sm, these structure are kind of known at least to some extent, using either using this mapping cone method or using the Postnikov decomposition of the spaces. So we in the next talk we'll see some of the examples of these groups, how the computation of these groups helps in saying the classification problem in the vibration or some extension or like uh, extension of map problem, how these groups helps there. Okay, so I'll stop here. So maybe we'll talk in the next of the remaining thing.
Yeah, so yeah, so since there is no one today,
Yeah, yeah,
so
okay.
yeah, maybe we can continue on next Tuesday. Next Tuesday we can start at the same timing, 4 p.m. So
Yeah, yeah, sure, sure.
okay, so I'll stop recording.